Look at this transverse sine wave. We immediately perceive the distinct shape of crests and troughs traveling horizontally at a constant speed. Our visual processing naturally tracks these peaks and valleys as they propagate forward through physical space. The horizontal progression is strictly spatial, governed by wavelength, lambda, and the angular wave number, k. Wavelength is the minimum distance between 2 points having the same phase, while the wave number, k, represents 2 pi times the number of waves accommodated per unit length. But the visual of a traveling shape is slightly deceptive. The physical medium, the actual material of the string, is not traveling to the right along with those peaks. Instead, every individual particle making up that string is moving along a strictly temporal dimension, oscillating up and down in place. How do we isolate and measure this internal, stationary rhythm when the macro shape of the wave is constantly shifting across our field of view? To calculate the temporal mechanics of a wave, we have to stop tracking the overall shape and shift our perspective to the micro-movement of a single constituent particle. To define the nature of frequency and period, we must mathematically freeze physical space, forcing us to look exclusively at the passage of time. This standard mathematical function describes the displacement of a transverse traveling wave. Y of x and t equals a sine of kx minus omega t. To find exact displacement, it demands 2 inputs, a physical location, x, and a specific moment, t. We can eliminate the spatial variable by locking our attention onto one specific point on the string. We will choose the origin point, where the position x is exactly 0. Setting x to 0 has an immediate mathematical consequence. The entire spatial term, k times x, evaluates to 0 and drops out of the function. The equation simplifies to y of 0 and t equals negative a sine omega t. This isolated equation now calculates vertical displacement based on a single changing variable, the forward march of time. Physically, we are now observing a single constituent of the medium oscillating up and down on its own vertical axis. This particle is executing simple harmonic motion. Simple harmonic motion is a type of periodic motion where the restoring force is directly proportional to the displacement. The motion is bounded by physical limits. It reaches a maximum positive amplitude, represented by a, and a maximum negative amplitude, represented by negative a. Even though the particle's physical location on the horizontal x-axis never changes, its position in time is constantly advancing as it cycles between these amplitudes. By mathematically freezing space, we have stripped away the illusion of forward travel. Underneath the traveling wave is a simple oscillator ticking like a clock. We measure the cycle of this clock using a metric called the period, represented by the capital letter T. This graph maps displacement against time. The period is the duration it takes for our isolated element to complete one full up and down oscillation cycle. We begin tracking the particle at its starting position, time 0. As time progresses, the particle moves through its maximum positive amplitude, passes back through equilibrium, and reaches its minimum amplitude. The moment the particle completes the cycle and returns to its initial phase state, the elapsed time is equal to the period, t. We can connect this physical time interval directly back to the rules governing the sine function, negative a sine omega t. In trigonometry, a sine function repeats its exact value after every 2 pi change in angle. Because the physical cycle repeats after a duration of t, and the mathematical cycle repeats every 2 pi radians, these two values are equivalent representations of the same event. The total argument inside the sine function, omega times t, must evaluate to exactly 2 pi at the precise moment the time t reaches the period t. This introduces omega, known as the angular frequency. Angular frequency is the rate of change of the phase of a sinusoidal waveform. Because the full cycle is 2 pi, omega times t equals 2 pi. Rearranging this to isolate the period shows that t equals 2 pi divided by omega. This introduces a direct inverse relationship. A higher angular frequency results in a shorter oscillation period. We can also express this rate using standard frequency, nu. Frequency measures the number of oscillations per second and is measured in hertz. 1 hertz is equal to 1 cycle per second. Standard frequency is the exact inverse of the period. Nu equals 1 over t, which is equal to omega divided by 2 pi. The period and the angular frequency are locked together. If you know the time it takes for one cycle to complete, you mathematically know exactly how fast the wave's internal clock is spinning. These derivations have relied on the geometry of a transverse wave, visualizing a physical string moving vertically. But these rules of time remain consistent even if the physical geometry of the wave changes. Consider a longitudinal wave, such as a sound wave traveling through a column of air. In a sound wave, the constituent air particles do not move up and down. They oscillate forward and backward, parallel to the direction of wave propagation. Here is the displacement function for a longitudinal wave. We replace the vertical variable y with s to denote longitudinal displacement along the axis of propagation. Look at the argument inside the sine function. Despite replacing the axis of displacement, the temporal variables, omega and t, remain unchanged. The orientation of a particle's movement in space is irrelevant to its internal rhythm. The mathematical clock governing the period and frequency is universal across all mechanical waves. We began by observing the shape of a wave traveling through space and drilled down to isolate a single particle trapped in a cycle of time. A wave operates across two distinct domains. First, we have the spatial variables, wavelength and angular wave number. Wavelength and wave number strictly measure physical distance, determining the geometry between identical phases in the medium. Second, we have the temporal variables, period, frequency, and angular frequency. These metrics exist solely in the dimension of time, measuring the duration and the exact rate of the particle's internal oscillations. A complete mathematical description of a wave requires connecting these two domains. When we relate the physical spacing of the wavelength to the internal rate of the frequency, we can calculate the wave's total speed. The variables t, omega, and nu define the internal clock for every mechanical wave, from a pond's ripple to a sound in the air.